Sarah Walker here, and I'm going to illustrate a connection between squaring in math and geometry, squares and triangles via the Pythagorean theorem. So, starting out, when we say we are squaring something, we mean multiplying it by itself, right? So 2 squared is 2 times 2, which is 4. 3 squared is 3 times 3, which is 9, and so on, right? Okay. Well, what does that look like geometrically? Why do we call it squaring? Well, it's because if you have a line segment, say, that is 2 inches long, we'll pretend that these are inches. Those are a bit longer than inches, but suppose that this is 2 inches long. To square it, you literally make a square out of it. You take another line segment that's also 2 inches long, perpendicular to this. So this side is also 2 inches, and then make a complete square out of it. And when you do, you have 4 squares that are each an inch across. So you had each square is 1 inch by 1 inch. So you originally had 2 inches, and when you multiply by another 2 inches, you have 1, 2, 3, 4 square inches. So 2 inches squared is 4 square inches. Notice the unit gets squared as well as the number. If I have a square that's, if I have a line segment that's 3 centimeters long, we'll pretend these are centimeters now, 3 centimeters, then I square it by taking a line, a segment the same length, and I make a square out of it, and so I end up with make my divisions in there, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares that are each an inch square, or centimeter. I went from inches to centimeters. 3 centimeters, 3 centimeters, 9 square centimeters. So 3 centimeters squared is equal to 3 centimeters squared is equal to 9 square centimeters, because I have 9 of them, and each of them are 1 square centimeter. That's why we call it squaring. So, when we have a right triangle, and we say that this is side A, and this is side B, and this is side C, and that the Pythagorean tells us, Pythagorean Theorem tells us that a squared plus b squared equals c squared. In other words, either of the short side squared plus either the long side squared equals the hypotenuse squared. If we have, say, triangle that is a 3, 4, 5 right triangle, then we can check that 3 squared plus 4 squared equals 5 squared. Well, 3 squared equals 3 squared plus 4 squared equals 5 squared is what the Pythagorean theorem is telling us. And if you multiply that out, you'd get 3 squared is 9, 4 squared is 16, and yes, that does in fact equal 5 squared, which is 25. So that's an example, one of the very few examples that the numbers work out to be integers, whole numbers. So geometrically, what this looks like is if I make a big room up here. If I make a square out of these sides, I'm going to just use this whole space. So there's my 3. There's my 4. 1, 2, 3, 4, and 1, 2, 3. And those could be inches, they could be miles, whatever they are. And then about the same size, 1, 2, 3, 4. Not very uniform. That's probably not really a 3, 4, 5 triangle, but we're pretending. 1, 2, 3, 4, 5. That's better. Okay. 3, 4, 5. There we go. Well, if I take that segment and square it, then I would have square same size. And I would literally have 9 squares. Those are supposed to all be the same size. If I square 4, then I would have 16 squares, all the same size. 1, 2, 3, 4 times 4, 16 of these ones. And over here, if I square the 5 side, I would literally have a square that's 5, length of 5 on each side. And so I have 5 by 5, 25 squares in my square. So literally 3 squared plus 4 squared, 9 squares plus 16 squares does equal 25 squares, which is 5 squared. Isn't that nifty? So what then does it mean to take a square root? It means I have a square and I want to know what's the length of just one side of that square. So this is a square that's 9 square units. The square root is the length of just one side, which is 3 square units. Square root of 9 is 3. Square root of 9 equals 3. Likewise, the square root of 16 is 4, because the length of just one side of a 16-unit square is 4. That's where I needed to stop, and I didn't come up with a clean ending for that one.